Chapter 4. Newton's first law of motion, inertia. If you saw a boulder in the middle of a flat field suddenly begin to move across the ground, you'd look for the cause of its motion. You might look to see if someone was pulling the boulder with a rope or pushing it with a stick. You would reason that something was causing it to move. We don't believe that motion occurs without cause. In general, we say the cause of a boulder's motion is a force of some kind. We know that something forces the boulder to begin moving. If we look at the picture, a huge oil tanker ship being pushed by a small tugboat. Because of its huge inertia, the ship is not easily pushed off course. Section 4.1. Aristotle on motion. The idea that a force causes motion goes back to the 4th century BC, when the Greeks were developing some of the ideas of science. Aristotle, the foremost Greek scientist, studied motion and divided it into two types, natural motion and violent motion. Natural motion on Earth was thought to be either straight up or straight down, such as a boulder falling toward the ground or a puff of smoke rising in the air. Objects would seek their natural resting places, boulders on the ground and smoke high up in the air like the clouds. It was natural, they thought, for heavy things to fall and for very light things to rise. Aristotle proclaimed circular motion was natural for the heavens, for he saw both circular motion and the heavens as without beginning or end. Thus the planets and stars moved in perfect circles around Earth. Since these motions were considered natural, they were not thought to be caused by forces. Violent motion, on the other hand, was imposed motion. It was the result of forces that pushed or pulled. A cart moved because it was pulled by a horse. A tug of war was won by pulling on a rope. A ship was pushed by the force of the wind. The important thing about defining violent motion was that it had an external cause. Violent motion was imparted to objects. Objects in their natural resting places could not move by themselves. They had to be pushed or pulled. Let's go back to figure 4.1. A child looking at a rock or a boulder. Do boulders move without cause? Of course not. It was commonly thought for nearly 2,000 years that if an object was moving against its nature, then a force of some kind was responsible. Such motion was possible only because of an outside force. If there were no force, there would be no motion, except in the vertical direction. So, the proper state of objects was one of rest, unless they were being pushed or pulled or were moving toward their natural resting place. Since most thinkers before the 16th century considered it obvious that Earth must be in its natural resting place, and they assumed that a force large enough to move it was unthinkable, it was clear that Earth did not move. At least that's what they thought. Section 4.2. Copernicus and the moving Earth. It was in this intellectual climate that the astronomer Nicolaus Copernicus, born in 1473, died in 1543, he formulated his theory of the moving Earth. Copernicus reasoned that the simplest way to interpret astronomical observations was to assume that Earth and other planets move around the sun. This idea was extremely controversial at the time. People preferred to believe that Earth was at the center of the universe. Copernicus worked on his ideas in secret to escape persecution. In the last days of his life, and at the urging of close friends, he sent his ideas to the printer. The first copy of his work, De Revolutionibus, reached him on the day of his death, May 24th of 1543. Section 4.3. Galileo on motion. Galileo, the foremost scientist of late Renaissance Italy, was outspoken in his support of Copernicus. As a result, he suffered a trial and house arrest. One of Galileo's great contributions to physics was demolishing the notion that a force is necessary to keep an object moving. A force is any push or pull. Friction is the name given to the force that acts between materials that touch as they move past each other. Friction is caused by the irregularities of the surfaces of objects that are touching. Even very smooth surfaces have microscopic irregularities that obstruct motion. If friction were absent, a moving object would need no force whatever to remain in motion. Galileo argued that only when friction is present, as it usually is a force needed to keep an object moving. He tested his idea by rolling balls along plane surfaces tilted at different angles. He noted that a ball rolling down such an inclined plane picks up speed. as shown in the left on figure 4.2. The ball is rolling partly in the direction of the pull of Earth's gravity. He also noted that a ball rolling up an inclined plane in a direction opposed by gravity, that such a ball slows down, as shown in the center of figure 4.2. So what about a ball rolling on a level surface, one that's not going downward and it's not going upward, as shown on the right in figure 4.2? While rolling, the ball does not roll with or against gravity. Galileo found that a ball rolling on a smooth horizontal plane has almost constant velocity. He stated that if friction were entirely absent, a ball moving horizontally would move forever. No push or pull would be required to keep it moving once it is set in motion. So here's figure 4.2. When the ball rolls downward, it moves with Earth's gravity and its speed increases. When the ball rolls upward, it moves against gravity, it loses speed. The in-between case is when it's rolling on a flat surface. So logically it would not speed up, it would not slow down, it would just keep rolling steady. Does the ball's speed change while rolling horizontally? Not if there's no friction. Galileo's conclusion was supported by another line of reasoning. He described two inclined planes facing each other as in figure 4.3. A ball released to roll down one plane would roll up the other to reach nearly the same height. The smoother the planes were, the more nearly equal would be the initial and final heights. Let's look at the picture real quick. So see the red ball here, if you release it, it rolls down, it rolls back up again and stops at nearly the same height. He noted that the ball tended to attain the same height even when the second plane was longer and inclined at a smaller angle than the first plane. In rolling to the same height, the ball had to roll further. Additional reductions of the angle of the upward plane gave the same results. Always, the ball went further and tended to reach the same height. So if you notice in the figure, the right-hand slope here, and then it gets less steep. Okay, so the ball has to roll farther to get back to the same height, which is what it does. If you made it even more flat, the ball would have to roll even farther and farther to reach the same height. So what if the angle of incline of the second plane was reduced to 0 so that the plane was perfectly horizontal? How far would the ball roll? He realized that only friction would keep it from rolling forever. It was not the nature of the ball to come to rest, as Aristotle had claimed. In the absence of friction, the moving ball would naturally keep moving. Galileo stated that this tendency of a moving body to keep moving is natural and that every material object resists changes to its state of motion. We call this property of a body to resist change inertia. Galileo was concerned with how things move rather than why they move. He showed that experiment, not logic, is the best test of knowledge. Galileo's findings about motion and his concept of inertia discredited Aristotle's theory of motion. The way was open for Isaac Newton to synthesize a new vision of the universe. Isaac Newton was born in 1642 and he died in 1727. Let's read this check question. A ball is rolled across a countertop and rolls slowly to a stop. How would Aristotle interpret this behavior? How would Galileo interpret it? How would you interpret it? Okay, so a ball rolls across a countertop and rolls slowly to a stop. Aristotle would say, hey, that ball naturally wants to come to rest, so it's just naturally stopping. Galileo would interpret differently. Galileo would say, no, the ball doesn't naturally want to stop, the ball wants to naturally keep going. So there must be friction acting from the outside, causing the ball to slow down and stop. I would interpret the same way as Galileo, because I believe in what he figured out.